This class, 12th standard, 3rd chapter current electricity and class number 7. We will discuss about dependence of temperature on resistance. I told you previously, when temperature increases, resistivity increases. When temperature increases, resistivity increases. If resistivity increases, resistance also will increase. Let R0 is the resistance at 0 degree Celsius. RT is the resistance at T degree Celsius. So what it means? From the value R0, it increased it to a value RT with a temperature increase of T degree Celsius. So there is a change in the resistance. It is found that the change in the resistance is proportional to R0 and also proportional to temperature change. So delta R proportional to R0 T, and delta R equal to a constant alpha into R0 T. This is proportionality and this is constant. Don't take it both as two, both are same, right? This is only proportional to and it's a constant alpha. So delta R equal to alpha R0 T. What is alpha? Alpha will be delta R by R0 T, which is the fractional change in resistance for unit rise of temperature. Fractional rise of temperature, fractional rise in resistance for unit rise of temperature, and we call it as temperature coefficient of resistance. Temperature coefficient of resistance. Now from this expression, delta R, you can write like delta R will be RT minus R0, right? That is equal to R0 alpha T, where T is the rise in temperature from 0 degrees Celsius. So RT equal to R0 plus R0 alpha T, or RT equal to R0 into 1 plus alpha T. This is the expression. Actually, the variation, more correctly, I should say like RT is equal to R0 into 1 plus alpha T plus beta T square plus etc. is there, where alpha, beta, gamma, etc. can be the coefficient, but all those other factors are very small, so that they are neglected. That is actually the more accurate result of it, but in our syllabus we need only to understand this one. So from this equation you can reach the expression for alpha also. Alpha will be RT minus R0 is equal to R0 alpha T. So alpha equal to RT minus R0 divided by R0 alpha. This is the expression for, R0 T. This is the expression for temperature coefficient of resistance. Now, problem may be asking in another mode, like at T1 temperature, resistance is R1, and at T2 temperature, resistance is R2. Ready? Now, they may be asking what is the value of alpha. Under that situation, you have to use alpha equal to R2 minus R1 divided by R1 T2 minus R2 T1. This is the expression when alpha is asked with two different values of resistance is given at two different temperatures. Now, as there is expression for resistance, there is expression for resistivity also, like rho T is equal to rho 0 into 1 plus alpha T. Same expression. Same expression is there. Now, I told you this is the actual variation. So actually, when you write the expression for resistance and temperature graph, the graph will be something like this. Very high temperature, at very high temperatures, these factors will be coming up so that the graph will not be straight line. But when we consider this expression only, what RT equal to R0, like this expression only, RT equal to, this is actually the expression within our syllabus, right? R0 plus R0 alpha T. This is just like, this is Y, this is resistance at temperature T. This is Y, and this is C, and this is X temperature. So it is slope. So under that situation, the graph coming out will be, when you write the graph between resistance at temperature T and temperature at the x-axis, the graph should be a straight line according to this expression. Now that will be the value of that will be the nature of variation of the resistance. The slope will be giving R0 alpha, and this is the y-intercept, which is the value of resistance at 0 degrees Celsius, which is R0, right? And the slope of this graph, if it is theta, and that slope of the graph tan theta will be equal to R0 alpha. This is what the variation of resistance of a metallic conductor with temperature. And I told you in the previous class, for semiconductors and insulators, the resistance decreases with temperature. That we will study in the chapter semiconductors at the end of the year, right? Okay, thank you.